So hi, my name is David Buck. I'm from the Java Sustaining Engineering team here at Oracle. I mostly fix JVM bugs, usually JRocket bugs up until now. I'm also, when I'm not fixing JVM bugs, one of the project maintainers for the OpenJDK 8 updates project. So sometimes you can find me arguing with people online on various public aliases about what should or should not go into JDK 8. And when I'm not working, I'm usually still sitting behind a computer coding. And for extracurricular activities, I tend to like to do talks like this, especially if there's some sort of free food involved. So today we're going to talk about Java debugging. So I'm going to cover just a brief overview of what the architecture, the overall architecture is. And then we're going to dig down into the wire protocol and the JVMTI side of the talk. So just to jump in and kind of talk about the gigantic elephant in the room, when we first found out which talks did and did not get accepted, that was kind of when I went to kind of start making my slide deck and everything. And I went and I said, okay, so what did I promise them that I would talk about? So I want to go see the description I submitted. So I go to the course catalog and I look up my debugger under the hood, and I'm very surprised to see that there's actually 2 debugging under the hood talks scheduled for Java 1 this year. So just so I have an idea of who I'm talking to, how many people actually got to see Martin's talk yesterday? Wow, okay, way less than I expected. Okay, so there are 2 talks this year, and ostensibly about the exact same issue. And to my utter horror and dismay, Martin's talk is like really, really good. So he set the bar rather high for this topic. So what to do? So ideally, we don't want to have too much overlap, right? There's, both people should be able to attend both talks and really not have too much time wasted with redundant information. So what we decided to do was, his talk was primarily focused on the JDI side of the debugging architecture. So I was going to kind of take everything else, kind of the lower end. And if these kind of terms don't seem to make a whole lot of sense to you right now, don't worry, that's kind of what we're going to cover in these talks. So ideally, you should really see both talks. Each of these talks by themselves kind of leaves a whole piece of the picture uncovered. But luckily, it's available on his talk, a previous version of his talk that he did is available on YouTube, and his slide deck is also up. So I have links to a previous version of his talk that he did at the resource section of my slide later. So I encourage everybody who wasn't lucky enough to catch Martin's talk live yesterday to go check out what he said on YouTube, because it'll really complement what I'm going to talk about today very well. That said, you don't really need to see his talk before mine or vice versa to get everything. I made all my slides and my content assuming that a very large portion of the people watching today will have not seen his talk. So we'll kind of just tackle things in any order we feel like it, and hopefully get a complete picture at the end. So if you're, I'm throwing around these terms like JDI and JVMTI and JDWP, and I think maybe not just a few people here really aren't familiar with what those terms are or what they mean. So we're going to go in and try and shed some light on that and go into the details of what the architecture actually consists of, what the different components are. So these are all part of something that is known as the Java Platform Debugger architecture. And it's something that's been around, as far as I can tell, maybe around since 1.3. There were technologies that were parts of it that predate that, but just kind of doing some Google searching and looking at the Wayback Machine archives, it seems that we started maybe calling the whole thing that we put all these pieces together, the JPDE, somewhere around 1.3. And so let's dig into what this actually is. So the idea was that we would have this kind of comprehensive framework for writing debuggers and debugger-like tools for the JVM, and there were certain goals that we had to try and accommodate when we did this. One thing, of course, is that obviously Java is, we think, a really great language to write just about everything in, and that would include debuggers themselves. So we want to make it easy for people to be able to write their own debugger or debugging-like tool in the Java language. We also want to make sure that the impact that the debugger has, or the act of debugging has, on the target JVM or the application running on that JVM is as absolutely small as possible. You want to avoid the observer effect, of course. And we also want to be able to allow a level of detail that would not normally be accessible to say, an external tool like that. So obviously, the kind of things we want to avoid are these Heisenbugs, right, where there's the observer effect, where by attaching a debugger and setting a breakpoint, or watching certain fields in a particular object, you actually change the behavior. And by running the debugger on top of the same runtime as the application you're trying to debug, it's going to be very hard to kind of avoid that. So this is what I kind of refer to as a strange loop problem, where there's a bootstrap issue of, how are you cognizant of what's happening at the lower level when you're dealing with a higher level of abstraction? Meaning it's very hard to kind of get JVM or native level details about the environment that you're trying to debug or profile when you're actually running on top of that environment. And so these kind of goals lead to somewhat contradictory design decisions, at least seemingly contradictory at first. So first, to enable people to write debuggers in Java, we need a Java-based API, and that's what JD is, the Java debugger interface. So we need something that people can write against in Java. And then, of course, we also need to make sure that we are low impact, so we need some way to do this from a remote process or an external process that's external to the JVM. At the same time, we want to provide all these neat little, kind of native level details, like things being able to iterate through the stack and things iterate through the heap and things like that normally wouldn't make sense to do from the Java level abstraction. So we need something that actually is in process. So these contradictions here. We want the best of both worlds. We want native, we want Java, we want in process, we want out of process. Well, why not both? So that's when we all celebrate. We host a little girl above us and cheer because we now have an architecture that actually gives us the best of both worlds, at the expense of perhaps a little bit of complication. So here's what the architecture looks like. And so the idea over here on your left is you actually have your application that you're trying to debug here running on the target JVM, and it is hosting an in-process JVMTI agent. JVMTI is the JVM tools interface, and we'll go into a lot more detail about what that means in some later slides. But there's this in-process API that allows us to kind of plug anything into it and get all sorts of nitty-gritty, low-level information. But it also, we have an implementation of a particular agent that speaks what is referred to as the Java debugging wire protocol, which is really just kind of a serialization of debugging commands and events that are sent back and forth between the debugging application here running as a separate process and the target JVM. So this, like I said, seems to have existed since at least 1.3. And one of the main keys here is that this is a modular design, that every single one of these three main components that makes it up, or three main APIs, the JVMTI, the wire protocol, and the Java-based debug interface, that these are all kind of interchangeable, and you can go and kind of plug in different components and technology into this and get some rather cool results with that. So, for example, we've actually changed one of the components of this around the time frame of Java 5, where the old native API, the old in-process API for collecting debug information that predates JVMTI was actually known as JVMDI. That was the debugging interface. And so that was available until Java 5, where we deprecated it and introduced the JVMTI interface, and then with Java 6 it was completely removed. But because we had this fantastic modular architecture and very clean separation between all the different components, we were able to just kind of completely replace the internal API wholesale with very little impact to the rest of the ecosystem and tools and things that people had already built against the other APIs. So we have this amazingly flexible thing. Another thing that we could possibly do or imagine someone doing is that you don't even have to be using JDI. So JDI is over here in the remote process or the debugger process, and it's the API that you write, you would ostensibly, if you're writing in Java, be writing against to kind of speak the wire protocol, so to speak. So you can think of JDI as like a translator between the API calls in Java that your debugger program is making and the wire protocol that the JVMTI agent is going to expect to receive. But this could not even be Java. Like anything could speak this protocol. So you could, in theory, write your own completely native application, you know, in just plain C or C++ or any other language, Python or whatever. And as long as you adhere to this wire protocol, you could interact with and control and debug a target JVM. So this, again, it's just an amazingly flexible thing. Another thing is that some of these technologies can stand alone, especially JVMTI. So there's a lot of use cases for JVMTI, and we'll mention a few of them today, where there's not a remote debugger involved. So for example, if you look at the demos directory in a JDK, you'll see a lot of examples of JVMTI plugins that will do things just if they get, like, if you try and send SIGQuit to get a thread dump, for example, they can, you know, produce an hprof dump or things like that. So there's all sorts of use cases for just having the internal in-process agent that doesn't have any dependency whatsoever on, you know, outside instrumentation or control. So another really interesting thing is that there's the new JShell tool that's coming out with JDK 9. How many people here have attended that talk? I know that, yeah. Okay, so JShell is really cool, and I don't know about you guys, but I'm really excited to be able to use that in my day-to-day debugging work and playing around, especially for like learning new APIs. And JShell, even though it's not a debugger in any real sense, it fits very nicely into the debugger architecture we have. So the implementation of JShell is that it actually sits on top of JDI, just like a debugging tool would, and that's what it uses to kind of remotely, you know, run your code against this, against a separate out-of-process JVM. That's actually responsible for executing the snippets of Java that you enter into the tool. So it's an extremely flexible architecture that kind of has no end to the variety of things that you can do and expansions you can make. So the Java debug interface, and again, I'm not going to go into any real detail here because Martin did such a fantastic job on his talk. So I highly encourage everybody that didn't see his talk to check out the YouTube video and download his slides that I linked to at the end of this one. But basically, it's just it's a pure Java implementation, so you can kind of just, you know, have that write once, run anywhere convenience when you're writing a debugger tool, and it's been around for at least, you know, since at least Java 1.3, and it's extremely stable and battle tested and hardened and all that stuff, and so it is very reliable and easy to use. So we're just going to kind of skip that part of the API and dig into the other two major components of the debugger framework, which is the wire protocol and JVMTI. So the wire protocol is really, really simple. In fact, it's amazingly simple. We can kind of cover it in just a few minutes. And one of the things that makes it so simple is that it doesn't specify a transport. So that you need something else on, like, underneath it, whether that be like, you know, IP for, you know, a socket connection, or for on Windows, the reference implementation supports in-memory as a transport for, you know, just mapping shared memory between the target and the debugger processes and using that to communicate. But we actually have a service provider interface, so you could code your own transport mechanism that this would work on top of. But it's really just kind of a dumb serialization at the bit level of what the different kind of commands and events that a debugger would need to use to communicate with a debuggy JVM. And if you look at the spec, you'll notice, and you're familiar with JDI, you'll notice that it's kind of like just a direct one-to-one mapping of the JDI Java doc. So if you look at the JDI Java doc, and you can be like, oh yes, so we have, these a virtual machine class here, and then there'll be a whole bunch of commands, and each subcommand mapping to a particular method of the JDI API. So it's really kind of it's easy to understand it. If you understand JDI, then JDWP, you can see what's going on very easily. So again, from the wire protocol's standpoint, it doesn't really care who's talking to it or who it's kind of attached to, so to speak, in the sense that the debugger, it can be written or implemented in anything as long as it's kind of speaking the protocol in some way that it understands. And the target JVM doesn't actually need to really be using JVMTI, because that's also another implementation detail that's abstracted away from the wire protocol level. So obviously, HotSpot, IBM's J9, BEA's JRocket all supported JVMTI, but you could imagine a Java SE implementation that might perhaps choose, for whatever reason, to not offer that kind of API to its users, the JVMTI API. And so they could just implement their end of the wire protocol directly without having to have the man in the middle of the JVMTI agent. And they might want to do that just to save on the cost of developing or kind of limit the options that the user has for whatever reason. So it's a really simple protocol. It starts off with a handshake. And the handshake literally is it just sends these 14 bytes in ASCII. The debugger comes out and says, hey, JDWP handshake. And probably not too surprising, the debuggy JVM responds with the exact same 14 bytes of ASCII text. And once you have this, you've more or less established a session. So now you have this asynchronous connection, virtual connection between these two entities, and they can send commands and replies to each other. So the protocol's really super simple, and the reason for that was to make it really easy to implement, even if you were writing your own implementation from scratch, for example. Like I said, if you wanted to, say, make a debugger in Python or something that would speak to JVMs, that would be aided by the simplicity of the wire protocol. So the headers, whether you're talking about a reply packet or a command packet, there's only two types of packets. The header is just 11 bytes, regardless of the packet type. So all packets have exactly the same header size, and then they may carry a data payload of some variable size. So just to see what they actually look like, so we have you can imagine the width here as being 32 bits. So we have a 4-byte length, and then a 4-byte ID for each packet, 1 byte for flags, 1 byte for the command set and command in a command packet, and then for reply we just have those 2 bytes are dedicated to an area code and their data. So the only difference between the two packet types is this kind of middle section here, where in the command ones we actually tell the target what we want them to do, and the other one represents kind of a response to that, what the result of that action was. So the length, this is actually the size of the entire packet, including the header, in bytes. And because it's a 32-bit number, that means we could have 4 gigabyte packets, which obviously is kind of almost ridiculous overkill. But the idea was just to have an extremely flexible format that would just never limit us, no matter how we wanted to kind of expand upon it or how people wanted to use it in the future. So you can have packets of really any size, and whatever transport you're going over is really going to be the limiting factor in how large of packets you could send. And then the ID also is a 32-bit number, and the IDs are just to tie the command, or you can think of a command as like a request, and the reply to each other. So each reply, by definition, is in response to a particular command packet that JVM has received. And so, and not all command packets have a reply. There's certain commands that don't require the sending of a reply. But for any that do, the only requirement is that the ID numbers have to match. But they don't have to be unique across, going for each direction in the channel. So what this means, because it's an asynchronous protocol, is you can actually have up to 4 billion different packets, in flight, so to speak, are being processed, meaning that they've been sent by one side, but a reply hasn't been received. So again, probably overkill, but it's just an extremely flexible protocol that makes sure that no matter how we try and expand it or add to it in the future, the protocol itself or the format's not going to get in our way. For flags, there's only one flag that exists as of today, and it just distinguishes between command and reply. So it's pretty simple and dumb. And then the command sets I'll go into in a second. So let's just go on those. So just to kind of reiterate, so we have all these different header fields. So the length, again, 32-bit value, that's huge, right? And it means that we could have gigantic packets. The ID field, again, 32-bit value, and it means that we have this amazing window of outstanding requests that haven't been acknowledged, so to speak, with a response packet. And we can have up to 4 billion, over 4 billion of them, 2 to the 32nd power worth of those. And the flagged ones, and this is just simply a way to mark packets as being either command packets or reply packets. And then the command fields are obviously where we get to interesting things. This is what these packets are actually telling the target JVM to do. And as I said before, there's pretty much almost a one-to-one mapping between the JDI API and the wire protocol. So the first 64 sets or command sets, each set's a byte, so there's 256 possibilities. So there's 256 possible command sets, but the top part of that address space, so to speak, is set aside for possible vendor-defined extensions, none of which actually exist that I'm aware of, but that's there if someone wanted to add an extension. And then the bottom half of that address space is divided between 64 that are kind of going in one direction from the debugger to the debuggee, and the other one is the debuggee back to the debugger. So when I say commands, it's not just from the debugger to the debuggee. When an event happens, like say for example you've hit a breakpoint or an exception has been thrown in the target JVM, the target JVM will use a command packet to asynchronously notify the debugger running on the debugger VM. So you have kind of a full duplex address space here, so to speak. But each one of these command sets more or less corresponds directly to a class in the JDI API. And then each one of the separate commands, which is also an 8-bit field, so we have 256 of those per class, so to speak, is the individual methods. And the error field these are just constants that are coded in as part of the standard, and you can look at them directly. The data is variable size. A lot of command types don't require anything. So for example, let's say I was going and I said I wanted to, in my debugger, I'm trying to check out the value of a particular field on a particular instance. Then I would send a request to send that, and I'd send the payload, so to speak, in that request would be the ID of the particular field that I'm trying to inspect, and then the response would be the value of that field that was being sent back. And again, if you look at this is actually the JDI. I'm sorry, no, this isn't. This is the wire protocol. But you can see the wire protocol. Each command set basically has there's a corresponding class in the JDI API called virtual machine, and it has methods that are very similarly named to these methods. Most of them, it's just a change of camel case to get these. So there's a direct one-to-one correspondence between the command sets and JDI classes, and then the individual commands and methods within JDI. So you can think of it as a really cheap, lightweight, thin serialization of the JDI API. So for transport, like I said, we don't actually define that or require anything in the wire protocol spec itself. And this has the somewhat unfortunate consequence of we have all this loose coupling between all the different components, but if your two components don't support the same transport, then you can't make them talk to each other. So in practice, the debugger program, whether that's something written in Java running on top of a JVM or something completely different, it needs to agree with and speak the same language, so to speak, to be able to set up a connection with and communicate with the target JVM. The current ones that the reference implementations support are on Windows only, we have a shared memory transport, and then on all of our supported platforms for Oracle SC, we have the socket transport. Notably, the JVMTI agent still doesn't support IPv6, although the Java side of the equation, the JDI implementation does. So I was just kind of showing you the kind of limitations that you can hit because of the lack of requirement for transport there. But also the other way of looking at that is that it gives you a lot of flexibility to kind of roll your own implementations and stuff. So this is probably one of the more important slides of this entire talk. The wire protocol is inherently insecure. It's not intended for real use in a production environment. I've been kind of shocked to see certain users or customers that will set up the JVMTI wire protocol agent and have it running in production, on the off chance that something would go wrong in their production environment, and they'd want to be able to attach with a Java debugger and try and either work around some sort of issue or even resolve it by just using debugging commands. I think that's just a very unlikely scenario to actually take place in real life. I don't think that, I've never actually heard of anyone successfully doing that. Usually people would just want to try and reboot or something or handle the issue some other way. But also it's a huge security risk. There's no authentication whatsoever on the wire protocol. So if you set it up and say, I want to listen on this socket, that means anyone can connect to it without any authentication. And it's absolutely trivial once you have, kind of debugger access to a JVM to completely own the system. The only thing you actually really need to do to execute arbitrary shell commands is you need to be able to set a breakpoint on a particular method that you are confident that target JVM is going to execute. So as long as if you know that they're running WebLogic Server, then you can just pick some particular method within WebLogic Server or even within like the NIO framework that will be called sooner or later, and then set a breakpoint on it. And then once you have that breakpoint, it's you own the system and you can run arbitrary code. And there's exploit proof of concepts available online if you Google for this. So if you have open to the world a debugging wire protocol socket, then you are basically saying, please run arbitrary code on my system. And yesterday, when I was putting the slide together, I went to Shodan and just searched, and there were even two instances of ones that were configured to send the outgoing handshake. So they were literally announcing to the world, please own me, run arbitrary code on me. So, but in practice, there's, I've seen this kind of, I would say, a terrifyingly high number of times in the field that people just kind of set this up and think it'll be convenient to have enabled at some point in the future, but don't really think about the security implications of it. Okay, so that's the wire protocol. Like I said, it's very straightforward and simple. It's just kind of a dumb serialization of the JDI API. Probably the more interesting part of this talk is the tool interface, because that's really what lets us do all sorts of crazy things. So the understand the tool interface, you have to have a little bit of background of the history involved. And originally, there were two very different APIs, both of which existed from JDK 1.1, from more or less the very beginning, and met with kind of different amounts of success in terms of usability and stability. There was the JVM debug interface, which I had already mentioned. It's the thing that we replaced in JVM or in JDK 5. And it was fairly stable, and actually it's the parts of JVMTI that come from JVMDI are very similar. So it was not a very difficult migration for people to update their code to work with JVMTI if they had some pre-existing code that they wrote against JVMDI. The profile interface was unfortunately a dumpster fire. it had all sorts of problems. It was fairly stable and worked well with kind of the original VM, the pre-HotSpot VM. But once it was ported over to the HotSpot code base, it was just never stable. It was very difficult to use with JNI, so you couldn't really mix JNI usage with it without a whole lot of effort. And it was very invasive into the design of the JVM itself. So basically what it offered you kind of all these really, at least seemingly convenient functions that you could call that would give you all sorts of interesting profiling information about what kind of objects were on the heap and histograms and things like that. But the problem is that meant that we had to actually implement that functionality for every single garbage collector. And so you would have cases where, yes, you could use the profiling interface to try and collect profiling information about your application, but then you'd be limited to this subset of garbage collectors that actually happen to support this particular functionality. So we had to actually add it to every single garbage collector that was implemented. And JIT compilation also, it didn't play with very nicely in all sorts of different circumstances, especially C2, it was not good. So if you can't do profiling running the JVM in a somewhat similar circumstance or configuration that you're going to actually run your code in production, then there's not a whole lot of value from the profiling data that you're going to pull from that. So it was unstable, it was hard to use, it was never officially supported, it was always labeled as experimental. It was just not a good solution. So the replacement here is obviously JVMTI. So around the Java 5 timeframe, Sun came in and said, okay, we need to have one ring to rule them all, so to speak. And so we'll have the single API. It'll replace both of these older APIs. It'll be officially supported. And they kind of learned from the mistakes that were made with the profiler interface and did things very differently. So this brings us to JVMTI. So like I said, it replaced the older two profiling and debugging interface. And so that naturally gives us a whole lot of interesting use cases outside of just debugging, and that's kind of one of the major points of this talk is that we have these really amazing and cool APIs and technologies, and so don't think about just debuggers, because there's already a whole lot of great debuggers that are already out there and that work really well. But there's a whole bunch of other kinds of tools that people haven't even thought up yet that these kind of APIs make possible. So there's all sorts of different things you can do besides debuggers with JVMTI. It's fully supported, unlike the profile interface was. And one of the most important things is that unlike the older debug and the profile interface, the ones that were replaced, it offers what I call pay-as-you-go performance impact, meaning that if you don't use specific functionality with it, you don't have the overhead, the performance overhead cost for that. And I'll go into more details about specifically what I mean by that in a few more slides. And the other thing to note about this that's very important is that it's based off of JNI. Just to get an idea here, how many people here feel comfortable like looking at JNI code, understanding it? Okay, so a fair number, maybe about a third. Okay, it won't be required for the coming slides, but it certainly would be handy. So for JVMTI, we write what are known as agents. And an agent is native code that runs within the address space of the JVM itself. So just like regular JNI code, you have to know what you're doing. If you make a mistake, you will very quickly bring down the entire JVM. What's interesting is that you can have multiple agents loaded and running all at the same time, and to at least as much as possible, they can be separated and not step on each other's toes to a large extent. You can even have a JVMTI agent that's statically linked into the JVM. So if you're like downloading the OpenJDK source code, you could use JVMTI to kind of have a hardwired agent of some kind that did some sort of either debugging or profiling or whatever you might want to do into your own specific build of the JVM. And it's launched from the command line with this flag, which I'm sure people have seen before, this agent lib thing. And so the idea is that you put the library name in here, and then you can pass an arbitrary number of arguments to the agent. So it's very flexible. You can give it startup commands and let it just interpret those however you want to program it to interpret them. it's kind of like almost like a separate command line utility. So this is the most common scenario, is where the agent will get loaded at startup time, and I'll go into why that's the most common scenario in a few slides. But that's not the only way that you can do this. Other ways are that it's perfectly valid to load a JVMTI library during runtime with system load library. And so you don't get exactly access to all of the functionality that you would get if the library was loaded from JVM startup, but you still get, that gives you an extra degree of flexibility for being able to kind of load it on demand. So just one thing, as I'm talking about agents here, I want to avoid confusion, because this is a fairly overloaded word, not just in the Java realm, but just in IT in general. There's all sorts of agents out there. So to be really specific of what I'm talking about when I'm talking about an agent here, I'm not talking about a Java agent. At JDK 5, there were actually two agent APIs, so to speak, that were introduced. There was the Java Lang instrument, that allowed us to do bytecode instrumentation, where we could replace the implementations of methods in classes and things like that, and do all this with pure Java implementations, which is really cool and really useful, and it deserves its own talk, but we're not going to cover that today. And that's loaded from the command line with the Java agent. So what I'm talking about with JVMTI is the other option, the native agent. And so the native agent is based off of the JVMTI API that we'll talk about in a few slides. And it's loaded with either agent lib or agent path. And these both basically have the same functionality. It's just the only difference is how they look up the agent. With agent lib, which is kind of the recommended way, the platform kind of default behavior in finding libraries is used to convert whatever name you pass it into, say, like on Windows, blah, 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 .dll. Or if you're on a Linux or Solaris, it'll be like lib, blah, 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 .so. So that kind of change or lookup it does automatically for you. Whereas an agent path, you would actually specifically give it a direct path or an absolute path right to the file that you want to load. So if you were on Windows, you would say, C:, blah, 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 .dll, and tell it exactly what to load. But pretty much the same thing. So this is what we're going to be covering. And in here, just in terms of the debugging architecture and the reference implementation for all this stuff, the JVMTI agent that we'll most often be working with, or the pre-existing one, is the Java debug wire protocol agent. So depending on the platform, it has a different name, right? So on POSIX platforms, you get the standard lib whatever so Windows, and then OS 10, as always, does things a little bit differently. But these are all basically the same agent, depending on what platform you are. But I can't stress this enough. This is just one kind of configuration or one kind of use case scenario. JVMTI can let you do all sorts of other amazing and cool things, in addition to just being kind of the mouthpiece for a debugger. In the same way that JDI is kind of a translator between your Java debugger application and the wire protocol, these agent libraries, these JVM agent libraries, are kind of a translation between the wire protocol and JVMTI. So probably the most important thing to really understand, or to be able to code against JVMTI, is to understand JNI, because it's based off of it. Some people will sometimes refer to it as an extension of the JNI interface or API, but it's not really technically an extension. There are some important differences, but the nice thing is that you can mix calls with them. So you can have JVMTI agents that use JNI, and that's pretty much expected. There's a lot of functionality in JVMTI that seems to be missing until you realize that no, the assumption is that you're going to be using JNI calls in addition to the new stuff that JVMTI makes possible. But like all the standard data types that we have in JNI are used in JVMTI. We use the same kind of strange modification of UTF-8 where we don't have null values and things like that JNI uses. So if you're used to coding in JNI, you'll be very comfortable and you'll be able to pick up JVMTI very quickly. If you're not used to coding in JNI, JNI itself is not that difficult to learn, but that's going to need to be the first step you take before you start taking on JVMTI agents. That said, there are some important differences. Just to do a brief review, though, of what JNI looks like, if I was to summarize JNI in like 3 slides, which is what I'm about to do here, and the most important thing is that there's an environment pointer, so to speak, and that is different for each thread, and it basically gives you access to a table of all pointers to all of the implementations of the different JNI functions. So most of JNI coding really is just about you get called, usually from the JVM, and you have that environment pointer, and then you use that to access the JNI functions, and that kind of lets you call back into the JVM and get things like the values of fields and make calls into Java and whatnot. So what does that look like at the code level? Usually most JNI code's written in C++ or straight C. This is a straight C example. I just want to point out, so it's just, we have kind of corresponding versions, JNI versions of Java primitive types. It's like a Java primitive double is now a J double in JNI speak, and then, but the key here is that this environment is being passed in, and then we use that to get access to the JNI API itself. So it's fairly straightforward, and if you're comfortable with C, it's not that bizarre of an API to use. You just have to make sure to do error checking very well. That seems to be what gets most people caught up. So that's JNI, and that's kind of what the JNI environment is. That you always hopefully have access to that pointer that can get you everything else. And similarly, JVMTI also has an environment that it takes the form of a pointer that you get handed, and that environment, as far as the information it contains, so to speak, represents the event callbacks, like what you want to do when a certain event happens. You express that by registering a callback. You enable or disable particular events that you are going to be interested in, the kind of events that you want to either instrument or profile in some sense. And we have capabilities that you can turn on and off, and I'll explain what capabilities are in just a second. And also there's JVMTI specific memory allocation and deallocation hooks, so that the libraries can be kind of managed by the JVM as they're loaded and unloaded. So one kind of very important difference between the environments, and this is why I say it's not purely just an extension of JNI, is that you basically have one environment per agent with JVMTI. So you can have as many agents as you want. There's no limitation on how many agents can concurrently be loaded by JVM and running and instrumenting code or doing whatever, but each of them has its own environment and only one environment, unless something's going horribly wrong. Whereas in JNI, you actually have a separate JNI environment per thread. So that's just an important thing that a lot of JNI programmers get caught up in when they start running JVMTI code. Now, capabilities, this is actually one of the core parts of the JVMTI API. This is what sets it apart from the kind of older and less efficient things. And basically, it's just a bunch of flags that say what this agent is allowed to do. So usually what happens is there's a negotiation between an agent when it's loaded, whether that be during JVM startup or dynamically if the library was loaded during the runtime, where the the agent will usually just start off and say, okay, so what capabilities do you support? Like, do you support capturing exceptions that are thrown, or do you support walking frame stacks and things like that? And so it'll ask the JVM what it supports, and the JVM will come back and say, these are the capabilities I support. And depending on what that agent needs to do, the agent might just decide at that point that, well, I can't really be useful on this JVM. This JVM doesn't support the kind of functionality I need, and so it might just bail. As very often is the case, actually, there's a lot of JVMs will run with they can run with a subset of all the possible options that they're capable of using. So they'll say that these options are required, and I'll refuse to load if I can't get them. But these other capabilities, if they're available, then that's nice, and I'll use them. But otherwise, I can live without them. So it gives you this kind of what I had referred to earlier as the pay-as-you-go thing. Whereas an enabling certain capabilities. As the agent, the JVM says, I can do A, B, and C, and you say, okay, well, I want you to do B and C for me. I'm interested in those types of events and things. Only then, you incur the cost, and you only incur the cost, ideally, for the particular capabilities that you enabled. So it's a very powerful mechanism to allow you to it's not this all or nothing approach like what we used to have with Xdebug and the really old, the pre 1.4 versions of the debug architecture, where basically if you were saying debug, the JVM just ran completely in interpreted mode and were really, really slow because it just assumed that it had to make all of the debugging features and all of the profiling features available to you, whether you're going to use them or not. But capabilities says, you can probe the JVM to ask what it supports, and then you can tell it which of those you actually plan on using. Now, it's important to understand here that there's actually kind of two levels of cost, because just because you declare to the JVM that, hey, I'm interested in using this capability, that doesn't necessarily mean that you're going to use it, or that you're going to use it against all of the different kind of target entities that it could be targeted against. So, for example, you could say, oh, I'm interested in being able to iterate through the heap, but I only want to be, I only will iterate through the heap to collect some sort of, histogram or something like that under very rare and strange circumstances. So there is often a cost of just saying, just declaring a capability. For example, there might be certain optimizations that the JIT compiler will avoid to make sure that if you do come back and say, okay, I want to now enable this event, and now I actually want to use that will be available to you. But very often there's a very different level of overhead between just declaring the capability and versus using it. Another thing that's very different from JVMTI versus what we had with the previous APIs was that it depends very, very heavily on bytecode insertion. Or BCIs, people will argue till they're blue in the face about whether it's bytecode injection or bytecode instrumentation or bytecode insertion, and I don't think many of you, and certainly I don't care which of those is actually correct, but basically it's a way to stick bytecodes into methods. And so we can take a class file as we're loading it and modify it before the JVM actually gets its hands on it, even say before the verifier runs, and change things around. Or we can take classes that have already been loaded and are in use by the JVM and dynamically at runtime just arbitrarily change the class. Now there's limitations on that, of course. We can't change, like, say, the layout of fields and things like that, because we have to be able to guarantee that objects that are already on the heap are still valid even if we change the definition of the class. But what we can change is we can actually change the code in the methods. And we can't change method signatures, but we can change the implementation that they run. And this is very useful for things like, say, if we're going to profile something, say I want invocation counts of how many times a particular method is called. This API will allow me to come in and just create my own standalone class that has some static fields that represent invocation counts, and then I can use bytecode injection to inject an accessor at the very beginning, kind of like right after the prologue of each of those methods that I'm interested in profiling, that will increment those counters for me. So it really lets you do anything. And a lot of people look at this and they go, well, this is so much harder than, say, the original profiling interface was. And in a sense, they're right, because you have to kind of roll your own for everything. You have to be very familiar with how to generate correct bytecode and have it pass verification and all that other things. And so there is kind of a cognitive overhead that you as a developer who's using JVMTI has to deal with when you're trying to instrument things with bytecode injection. But the other side of that is that just because whatever you're doing is Java bytecode, it's automatically compatible with everything within the JVM. So it doesn't matter what garbage collector you're using, it doesn't matter what JIT compiler you're using or anything. It doesn't, in a lot of sense, as long as JVMTI itself is supported, it doesn't matter what JVM you're using. By definition, all of these technologies are able to run and understand Java bytecode. So by by rolling your own implementations for all this stuff and putting it into the application at points that you're interested in profiling or debugging or whatever, it lets you kind of speak the lingua franca of the Java ecosystem, and every JVM or runtime implementation understands that. So you no longer have the case where, like you had with the old profiling interface, where you're limited to only a subset of particular Java collectors that we bothered to implement that functionality in, because it doesn't actually depend on other functionality within the JVM. The only thing it depends on is the JVM support of JVMTI, which says you can stick new bytecodes into pretty much any method. And it also lets you do, there's so many other use cases outside of this. There's fix and continue debugging, where you could actually, some IDEs would allow you to actually, modify the implementation of the method, replace that without restarting the system, and then just keep running and continue debugging. So it's kind of the sky's the limit. So what does an agent actually look like when it's being used? So there's an initialization phase when it starts off, and there's two functions that will get called automatically. If it's one that if you specify it on the command line, the onload load will get called, or if you attach it dynamically at some time during the runtime, then onAttach will get called. But both of these functions basically have the same role. Their job is to kind of initialize and set up the agent. And so when we're being set up, what we want to do is we want to kind of ask the JVM, okay, so what capabilities do you support? And then JVM will tell us, and then we'll decide if we want to continue or not. If we do want to continue, then we'll ask the JVM for a specific subset of those capabilities, maybe all of them, who knows. Then we'll actually say, okay, so for particular events that I'm interested in, the way that as an agent, I'm informed to those events is that callbacks are called by the JVM. And so I have to actually register my callbacks during initialization, and then I enable particular events, and all of this can change dynamically. So later I could be interested in one event during the beginning, like warm-up phase of my application, and then later I could be like, I'm no longer interested in those events, I want to look at a different event or whatever. So all this can be dynamically enabled and disabled. And then just it's kind of almost like a GUI event dispatch thread or something. You just kind of process your events as they happen, but they'll happen on the individual thread where the event occurred. And then finally, when the JVM shut down, usually, in most cases, because for most implementations, it's difficult to unload a library once you've loaded it. There's an agent unload where we could do things like perhaps persist data that we've collected to disk, or do anything else that we might want to, some housekeeping chore that we might want to do before the JVM dies. So a typical example of what this would actually look like in practice is most JVMTI agents have the model where they want to be active from startup. And the reason is because there's a whole lot of things that the JVM does when it's starting up that it wants to do differently if certain capabilities are enabled. So if you wait until the JVM is actually up and running Java code, it's too late to be like, okay, I actually wanted this capability, or I wanted this functionality. So you want to be able to get in there and declare, capabilities that would otherwise be disabled by the time the JVM got up and running. You also want to be able to change the environment. So say, for example, some agents, although I think this is rather odd, but they can go in and change the system properties. So they could do anything. They could modify files. The JVM literally is not even running yet. No classes have been loaded. No Java code has been executed at this point. So at the onload thing, it gives you this kind of primordial state of the JVM so that you can set things up to make sure that you're able to capture, profile, or debug everything. So even the most kind of basic classes that are part of what we refer to as the system classes. There's a couple dozen classes that are loaded at the very, very beginning, even before we start loading the standard classes that show version would load. And if you wanted to somehow instrument those or interact with the class loading, you would need to be in the very beginning. So a standard agent, or the most common form of agent, I guess, kind of does this. And so when it sets its callbacks, and then it sets just a few events to enabled. And the reason it does this is because there's actually a lot of limitations of what you can do. For example, you really can't call most JNI functionality because the JVM's not running yet. So you kind of set up what you want to do and kind of put everything in place. And then usually they'll register like thread death, VM start, and VM init seem to be the big three. But kind of the one we're most interested in is VM init, because that's when the VM comes back and says, I'm actually started and I can run Java code, and I'm awake now. So then we return from onload. Then we get called back from the VM, hopefully immediately, to say that the VM is actually started. And that's when we can go on and kind of turn everything else on and really start doing whatever it is that agent wants to do. And again, of course, when we actually are unloaded, there might be some kind of cleanup that we want to do. So we can actually look into and see all of this when it's happening on the VM. There's a really nifty option. It's like one of many. I mean, HotSpot has well over 1,000 different options, almost all of which are undocumented. And one of those undocumented options, or barely documented options, is this trace JVMTI. And it'll show you, usually what thread that the processing is running on, or even before, like when you're being run from the primordial thread, before the JVM's even really up and started. And it can show you basically everything about the interaction that the JVMTI agent is doing. It's very simple to use. You just have this on your command line, and then you have one or more descriptors, which I will describe. So a descriptor basically has 3 separate fields. There's actually no spaces between them in practice. The domain says kind of what you're interested in. Like, so you can say all calls to a particular function. If you name that particular JVMTI function in there, then this descriptor will catch all of those. There's kind of strange how you have func, which is all the major functions, and then like every function's a function, but not all functions are functions. So it's kind of an Orwellian thing going on there. But you can basically specify what types of events or interactions across this API boundary you're interested in getting debug out input, and then you can add or remove tracing to that. And the reason why you'd want to be able to remove tracing is that you might want to use, in a previous descriptor, you add everything, and you're like, I want everything except this one little part. That happens very frequently, and I'm not interested in. So by kind of combining multiple descriptors together and adding and removing in chunks, you can really narrow it down to exactly what you want to trace. And then for each individual interaction or event, for lack of a better word, you can say, okay, so what do I want to actually send to the standard out about this? And so I can see what the agent's passing in, what it's returning, all that stuff. So I wouldn't really go as far as to call this a demo, because it's really a pretty straightforward thing. But let's say I just have a simple, I just have some Java program that does nothing but calls thread sleep. And but it has this enabling. So it's basically saying I want to enable everything, and I want the input, I want the event data, I want just all the data that we can possibly trace for JVMTI. And I'm loading the wire protocol agent. So this is something a lot of people are interested in, because they want to know, okay, so if I don't use it, there's no part of this demo that includes a debugger. I'm not actually going to attach to it, but just the fact that I'm starting the JVM with the wire protocol agent, there's going to be a cost to that, because certain capabilities are enabled. And so you can see here that right off the bat, so the agent is querying the JVM, saying, okay, what are you capable of? And the JVM responds with some subset of capabilities. And then we go ahead and add those based off of what it said. We've obviously decided that we'll continue. And then we wait till the JVM actually starts up. We set our callbacks, wait till it starts up, and then we go ahead and enable a whole bunch of new events that we're interested in. But this, if we see, just one more minute. So if we see when we actually ask for the capabilities, this is fairly hard for a human to read, but each capability is represented by a single bit in this struct of ints here. So to actually make sense of that, or it's you can kind of take it apart by hand, but I've done that for you in this particular case. So we can see what the debugger depends on. And we can see that the required ones there's quite a lot of capabilities that we require, but there's also a whole bunch that are optional and we may or may not have. And this goes back to the final topic, and we're about 30 seconds out from the end here, but around the time of Java 1.4, Sun came out and said that we now offer full-speed debugging, meaning that you can enable debugging and basically, I don't know, if I read this, I kind of think that they're saying that there's no cost. And this isn't exactly true. The idea was that, with 1.4 or 1.41, depending on which of the two JIT compilers you were using, that there would no longer be an overhead to running a debugger. And this is kind of where I think we saw a whole bunch of users start just randomly enabling the wire protocol, the debug wire protocol in their environments without thinking about the security implications or the performance implications. So, okay, is it really full speed? This is because I really wasn't sure about the intellectual property implications of the spotted, or the winter owl or whatever, the snowy owl that is usually associated with this meme. But it's kind of doubtful. It's hard to believe that this is really full speed. And in fact, the reason that they called it full speed was just because compared to what it used to be, it's so much faster. It's several orders of magnitude faster. Because what used to happen in the battle days of 1.3 or before, 1.3 with HotSpot, you expected to JIT compile all of your hot methods. But if you told it that you were going to use debug, if you're using this like xdebug flag, which today is more or less just a no-op, it would basically disable all of your JIT compilation, so you'd be running in a pure interpreted mode. And the JVM did that just because it wanted to be prepared just in case you set a breakpoint in some method at some point. So when they say full speed debugging, what they mean is that after 1.4, pretty much all of your methods except a method that you set a breakpoint in will be JIT compiled now. So relatively speaking, it's almost as fast. But again, we're still setting up all these capabilities even if you don't attach with a debugger. Just by loading the JVMTI library, all these capabilities are enabled by the agent. So these capabilities do have a cost, and we have seen users hit those. For example, very heavy use of reflection can sometimes trigger certain edge cases where there's performance repercussions to having those capabilities enabled, even if you're not doing debugging. So usually there's not a noticeable impact, but there's no guarantees. There's no such thing as a free lunch. So wrap up, final slide. I just really wanted to point out, I'm obviously not going to be able to talk to you for 50 minutes and have you just immediately go out and start writing JVMTI code or writing a client for the wire protocol or anything like that. But hopefully now you have a sense of how the three different components of the debug architecture now fit together and what you can do with them, so that if you did want to write a JVMTI one, or if you're interested, you would know, where to start, so to speak, and where to look for more information. But one of the things I want to stress is it's not just for debugging. There's so many different things. One of the things that when I was preparing for this talk, I was surprised is when I started telling people I was going to do a talk about this, so many people told me stories about JVMTI clients or agents that they wrote. And it seems like it's a lot more common to write like one-off agents, just for a particular strange troubleshooting scenario that someone came across than I ever anticipated. So it's much more flexible and useful than I think people realize. And so there's a lot of power there. So just be aware of it, because you might run across a situation where you want to go and explore it more and use it. These are the resources, especially Martin's talk. I highly recommend it. He has a lot of really fantastic demos. Really enjoyable, and he does an excellent job of explaining JDI and some of the basics of debugging and what the different IDEs offer. So definitely have a look at all this stuff. And Kelly O'Hare's blog also is very worth reading. There's a whole bunch of great JVMTI articles. Thank you very much. I very much appreciate your patience.